Have you ever just paused and wondered how your computer actually understands the code you write? It really can feel like magic, right? But underneath it all, there's this really fascinating and honestly elegant process going on. So today we're going to pull back that curtain just a little bit on one of the most fundamental ideas in all of computer science, syntax-directed translation.
It all kind of starts with a simple question. When you look at something like 3 times 5 plus 4, your brain just instantly knows the order of operations. You do the multiplication first, then you add the 4. But how does a computer figure that out? To a machine, that's just a sequence of characters.
Well, to answer that, we've got to explore how a computer builds a bridge, really, from our human way of thinking to its own language of machine instructions. It's a journey from simple text to actual meaning. And it all begins with finding a kind of hidden structure.
Yeah, so to a computer, that expression, it isn't math. Not at first anyway. It's just a string of symbols. There's a 3, a space, an asterisk, another space, a 5, and so on. There's no built-in hierarchy, no sense of order. It's just a flat list of characters.
So to make any sense of this list, the computer's first job is to find a hidden blueprint. A blueprint that's buried inside those characters, one that reveals the code's true structure and what it's trying to do. And that blueprint, well, it has a name. It's called a parse tree. And this is the absolute first, most crucial step in giving our code some meaning.
Okay, so let's take a closer look at what a parse tree for 3 plus 4 actually looks like. It might seem a little intimidating, but the idea is actually super simple. See how the numbers, the 3 and the 4, are right there at the bottom? They're like the leaves of the tree. And the plus sign, our operation, it sits just above them, kind of like a parent. This structure, which is all based on the language's grammar, makes it perfectly clear how all the pieces relate to each other. It's basically a grammatical skeleton for our code.
Now, having this structure, that's essential. This is the syntax part. It tells us how the pieces are supposed to fit together. But, this skeleton, it doesn't have any life in it yet. It shows us there's an addition that needs to happen, but it hasn't actually done the math. Not yet.
So, to get to a final answer, we have to add another layer of information. We need to start attaching little notes or labels to our blueprint that tell us what to do at each step. In computer science, we call these little notes attributes.
You can literally think of an attribute as a little sticky note that we stick onto each part of our tree. And this note, it might hold the numerical value of that part, or maybe its data type like integer, or really any other piece of information we need to carry along for the ride.
Okay, so here's where it all comes together. Look at the bottom of the tree again. Each number has a sticky note, an attribute, with its value on it. Now, watch what happens as we move up. We just follow a simple rule. For a node that represents addition, we grab the values from its children and we add them. That sum then becomes the new attribute, the new value for the parent node. We just keep doing this, step by step, climbing up the tree until we get all the way to the top with a single final value. And that's it. That's how the computer actually calculates the result.
All right, so now that we get how a computer can evaluate an expression, let's take this idea a step further. Because this same technique of walking through a structure and applying rules can be used for something even more powerful: translation.
And that right there brings us to the official name for this whole process: syntax-directed translation. It's syntax-directed because the structure, the parse tree, guides everything we do. And it's a translation because we're using that structure and our rules to convert our code into something else entirely. This slide is a fantastic example of that translation in action. On the left, you see code that's easy for us humans to read. But on the right, it's been translated into something called 3-address code. Now, this format is way easier for a computer to handle because it breaks down complex stuff into simple, one-at-a-time steps. First, it does the addition and stores it in a temporary spot called T. Then, it uses that result in the very next step. See? It's a much more machine-friendly version of the original code.
And it turns out this whole idea of using grammar to guide a translation is just incredibly powerful. Its applications go way beyond just simple compilers. It's a foundational pattern that you start to see in so many different corners of computer science.
I mean, it's the core engine inside every programming language, of course, but it's also used in typesetting systems like TeX to turn simple text commands into these beautiful documents. And what's really cool is that students have used these exact same techniques to build little languages for all sorts of things, like music synthesis or creating custom behaviors in video games. When you really zoom out, you start to realize this isn't just about code. It's about a really fundamental way that we create meaning out of symbols. So if you take one thing away, let it be this. At the end of the day, it's just this simple formula. We find the hidden grammatical structure in a bunch of symbols, and then we apply a set of rules to that structure. And that combination, structure plus rules, is what gives us meaning. Whether that meaning is the number 7, or a sequence of machine instructions, or a perfectly typeset page.
So I'll just leave you with this little thought to carry with you. Where else in our world do we find these hidden structures that create meaning? If you look around, I think you'll be surprised at how often you find this exact same pattern. Thanks for joining me today.